Pick up almost any object built to move, seal, flex, absorb impact, or survive vibration, and there is a good chance synthetic rubber is hidden inside it. It may be in the tread of a passenger tire, the hose carrying coolant through an engine, the gasket sealing a pump, the weather strip around a door, the sole of a shoe, the membrane on a roof, or the stopper in a medicine vial. Most of the time, nobody notices it. Rubber is supposed to disappear into the machine and keep working. But the modern synthetic rubber industry did not begin as a calm commercial expansion. It began as an emergency. In early 1942, the United States discovered that an industrial civilization built on wheels had allowed nearly all of its most important elastic material to come from plantations on the opposite side of the planet. Then, Japan captured the regions that produced most of the world's natural rubber. The result was not merely a shortage of automobile tires. A military airplane consumed roughly half a ton of rubber. A tank required about a ton. A battleship could contain more than 75 tons in cables, seals, shock mounts, hoses, insulation, life-saving equipment, and countless parts that had to bend without breaking. Soldiers needed rubber in boots, gas masks, rain gear, medical equipment, vehicles, pontoon bridges, and communication systems. Steel gave the war machine its strength, fuel gave it motion, but rubber allowed its moving parts to survive. America had stockpiled natural rubber, but the reserve could not last through a long global war. The country had promising laboratory substitutes, yet almost no capacity to make a general-purpose synthetic rubber at the required scale. In 1941, American output of the material that would become the backbone of the program was measured in only a few hundred tons. Within 4 years, production had risen to roughly 70,000 tons a month. That transformation required the construction of an entire chemical industry, while the nation was already trying to build aircraft, ships, tanks, explosives, refineries, and aluminum plants. Companies that normally guarded patents from one another were ordered to exchange information. Chemists who had spent years competing began meeting around the same tables. The government financed dozens of plants. Petroleum refiners learned to make a strange reactive gas called butadiene. Tire companies learned how to turn a difficult, slippery polymer into reliable military tires. Universities investigated molecules that most Americans had never heard of. The wartime product was called Government Rubber Styrene, or GRS. After the war, it became known as Styrene Butadiene Rubber, or SBR. It was not a perfect imitation of natural rubber. In some applications, it was worse. In others, it could be better. Most importantly, it could be made from industrial chemicals inside the United States. Today, depending on how analysts define the category, the global synthetic rubber market is valued in the tens of billions of dollars. The wartime emergency did not create every modern elastomer, but it established the manufacturing system, research culture, and confidence that synthetic rubber could be designed rather than harvested. The material built to keep American vehicles moving in World War II became the foundation of a permanent global industry. To understand why, we have to begin before the first synthetic plant. In a tropical world of trees, plantations, and a supply chain so concentrated that conquering a few islands could threaten the mobility of an entire nation. Natural rubber begins as latex, a milky fluid produced by certain plants. The most important source is the tree Hevea brasiliensis, native to the Amazon region. When the bark is cut carefully, latex flows into a cup. That liquid contains microscopic particles of rubber, a natural polymer made largely from repeating isoprene units. Once collected, coagulated, washed, and dried, it becomes the raw material that can be compounded, shaped, and vulcanized into durable products. For centuries, the elastic substance was a curiosity outside the regions where indigenous peoples used it. In the 19th century, industrial demand accelerated after vulcanization made rubber more stable in heat and cold. Telegraph cables needed insulation. Factories needed belts. Bicycles and automobiles needed tires. By the early 20th century, rubber had become a strategic commodity. The tree was South American, but the center of production moved to Asia. Seeds taken to Britain were germinated and distributed through the empire. Plantations expanded in Malaya, Ceylon, and the Dutch East Indies. The trees thrived, organized estates produced rubber efficiently, and Southeast Asia came to dominate world supply. By the late 1930s, the United States consumed about half of the world's natural rubber, while importing most of it from that distant region. This arrangement looked efficient in peacetime. Rubber arrived by ship. American factories transformed it into tires and industrial goods, and consumers rarely thought about geography. But efficiency had produced dependence. The same concentration that reduced costs created a single strategic weakness. There was another problem. No material could simply be substituted for natural rubber without consequences. Natural rubber has a remarkable combination of tensile strength, tear resistance, resilience, fatigue performance, and low heat buildup. When a truck tire repeatedly deforms under a heavy load, the rubber must flex millions of times without cooking itself from the inside. When an aircraft tire strikes a runway, the material must absorb enormous stress. When a tank track pad hits rock, the rubber must resist tearing and abrasion. Chemists could make rubber-like substances, but matching the full balance of natural rubber was much harder than creating something that merely stretched. A laboratory sample could look convincing and still fail in a tire after hours of heat, flexing, and load. Germany had learned this during the First World War. Blockade pressure encouraged German companies to produce an early synthetic called methyl rubber. It was expensive and inferior, and production ended after the war. Research continued, however. In the 1920s and 30s, scientists at E.G. Farben developed a family of materials called Buna. The name came from butadiene and natrium, the German word associated with sodium. One version, Buna S, combined butadiene with styrene. Reinforced with carbon black, it showed strong abrasion resistance and became a serious general-purpose candidate. American companies were also experimenting. B.F. Goodrich developed Ameripol. Goodyear worked on Chemigum. Firestone operated a pilot program for butadiene styrene rubber. Standard Oil of New Jersey investigated ways to manufacture butadiene from petroleum and maintained technical relationships with E.G. Farben before the United States entered the war. Other synthetic elastomers already existed for specialized jobs. DuPont's neoprene-resisted oils and chemicals. Standard Oil developed butyl rubber, valuable for holding air. Thiokol materials resisted fuels and solvents. This meant the United States did not enter the crisis without knowledge. It had recipes, patents, pilot plants, researchers, and specialized products. What it did not have was a proven system capable of replacing hundreds of thousands of tons of imported natural rubber. That difference between knowing how to make a material and knowing how to supply a nation would define the entire emergency. In June 1940, before Pearl Harbor, President Franklin Roosevelt created the Rubber Reserve Company. Its mission included purchasing and distributing rubber, building a stockpile, encouraging conservation, and supporting synthetic production. The danger was visible, but the timing of the catastrophe was not. Then the map changed with terrifying speed. Japan attacked Pearl Harbor in December 1941. In the following months, Japanese forces advanced through Malaya, captured Singapore, and occupied the Dutch East Indies. The United States lost access to roughly 90% of its normal natural rubber supply. A trade problem became a military emergency. At the moment the supply was cut, the United States held a stockpile of about 1 million tons and had been consuming around 600,000 tons a year in peacetime. War demand would be higher. The reserve bought time, but not enough time. The first response was to make every existing tire last. Civilian tire sales were stopped and then rationed. Drivers were limited in the tires they could own. Retreading became essential. A national speed limit helped reduce wear because high-speed driving built heat and shortened tire life. Gasoline rationing was not only about saving fuel, it also kept cars off the road and preserved rubber. In June 1942, the government launched a nationwide scrap rubber drive. Families searched basements, garages, farms, and shops. They turned in old tires, garden hoses, boots, raincoats, hot water bottles, rubber bands, and toys. Gas stations became collection points. The public produced an enormous mountain of scrap, estimated at about 450,000 tons. The campaign was emotionally powerful, but scrap was not the same as fresh, natural rubber. Reclaimed material could be used in retreads and less demanding civilian products, freeing better rubber for the military, but repeated vulcanization and aging had changed it. It could not solve the need for high-performance aircraft and truck tires. The scrap drive was a bridge, not the destination. Alternative crops were investigated. The government expanded work on WWII, a desert shrub that produces natural rubber. Fields were planted in the American Southwest. Researchers, including Japanese-American scientists confined at Manzanar, studied breeding and processing. Other tropical and temperate plants were examined. These programs mattered as insurance, but agriculture could not expand quickly enough to fill the immediate gap. The only answer that could plausibly reach the necessary scale was synthetic rubber, yet political and technical disagreements delayed a unified plan. Should butadiene come from petroleum or from alcohol made with grain? How much steel should be diverted to chemical plants? Which synthetic recipe should become the national standard? Who would control production? The rubber companies, oil companies, farm interests, Congress, and federal agencies all had different priorities. In August 1942, Roosevelt appointed a small rubber survey committee led by Bernard Baruch, with James Conant of Harvard and Carl Compton of the Massachusetts Institute of Technology. They were given 1 month to investigate the crisis. The committee's conclusion was blunt. Conservation alone would not be enough. Agricultural substitutes would not arrive in time. The nation needed centralized authority and immediate construction of 51 plants to produce the monomers and polymers required for synthetic rubber. This was the moment the emergency became a national industrial program. The number 51 can be misleading if imagined as 51 identical rubber factories. The program was a chain. Some plants made butadiene, others made styrene. Some polymerized those monomers into GRS. Other facilities produced butyl rubber, neoprene, and additional materials. Refineries, alcohol plants, carbon black factories, tire plants, testing laboratories, and transportation networks all had to work as one system. The government provided capital because private firms could not rationally finance so much emergency capacity under uncertain post-war conditions. Private companies designed, built, and operated much of the system because they possessed the specialized knowledge. It was neither a completely nationalized industry nor a normal private market. It was a government-owned, contractor-operated network built under wartime authority. The most important decision had already begun to take shape. On December 19, 1941, Standard Oil of New Jersey, Firestone, Goodrich, Goodyear, and United States Rubber signed an agreement to share patents and technical information under the Rubber Reserve Company. In ordinary business, these companies protected their formulas, processes, and test results. In the emergency, secrecy between American firms had become a liability. On March 26, 1942, company and government representatives agreed on a mutual recipe. The basic polymer would contain about 75% butadiene and 25% styrene. Water and soap would create an emulsion. Potassium persulfate would initiate the reaction. A mercaptan modifier would help control molecular size. The result was GRS. Choosing one recipe did not eliminate competition. It redirected it. Instead of each company trying to own a separate national solution, researchers could compare improvements against a common standard. A successful change in polymerization, carbon black, antioxidant, tire construction, or testing could be shared through the program. The collaboration became enormous. More than 200 patents were shared. The National Bureau of Standards worked on measurements and uniform testing. Bell Telephone Laboratories helped coordinate research. Universities in Illinois, Minnesota, Chicago, and elsewhere studied polymerization and molecular structure. Industrial laboratories investigated processing, compounding, and tire performance. Committees met repeatedly in Akron, the center of the American tire industry. This collective research was essential because the problem was larger than making rubber in a reactor. The material had to be consistent from plant to plant. It had to be shipped in standard bales. Tire factories had to process it on machinery built for natural rubber. Finished tires had to survive heat, speed, load, water, cold, and rough roads. A formula that worked in a glass flask was only the first inch of a 1,000-mile journey. The second great challenge was feedstock. Styrene could be produced from established chemical streams, but butadiene was needed in extraordinary quantity. It is a reactive 4-carbon molecule that can be derived from petroleum gases or produced from alcohol. The Baruch program used both routes. Petroleum companies built plants around refinery feedstocks, using catalytic processes to remove hydrogen from hydrocarbons. Alcohol-based facilities converted ethanol, including alcohol derived from grain, into butadiene. The debate between petroleum and alcohol was political as well as technical. Farm state advocates saw grain alcohol as a domestic resource. Oil companies argued for refinery integration and long-term efficiency. Wartime reality forced both methods into service. Delays in some petroleum facilities made alcohol-derived butadiene unexpectedly important during critical phases of the buildup. America was not simply manufacturing rubber, it was manufacturing the ingredients for rubber, the machinery for the ingredients, and the standards that allowed everything to connect. Inside a GRS plant, the process began with materials that looked nothing like a tire. Butadiene was a volatile gas under ordinary conditions. Styrene was a liquid. They were measured into a mixture of soapy water where tiny droplets dispersed through the liquid. The soap was not there for cleaning. It stabilized the emulsion, creating millions of small reaction zones. An initiator generated reactive chemical sites that opened double bonds in the monomers. Butadiene and styrene molecules began linking into long chains. This was copolymerization, 2 different monomers becoming one polymer. The reactor did not instantly fill with a solid block. It produced a milky synthetic latex, visually similar in some ways to natural latex. Controlling the reaction was difficult. If the chains became too long, the rubber could be hard to process. If they were too short, strength suffered. Temperature affected reaction speed and molecular structure. Contamination could ruin a batch. The mercaptan modifier helped regulate chain length, but operators still had to watch time, pressure, purity, and conversion. At the desired point, a short-stop chemical halted polymerization. Reacted butadiene and styrene were recovered because wartime feedstock could not be wasted. Antioxidants were added to protect the polymer from oxygen and aging. Next, the latex had to become solid rubber. Chemicals and salts caused the microscopic polymer particles to coagulate into crumbs. The material was washed to remove soap and residues, then dried. Automatic equipment weighed portions, and presses compressed them into bales. A wartime photograph from the United States rubber plant at Institute, West Virginia, shows the finished material leaving a dryer and entering an automatic weighing machine that delivered 75-pound charges to the baler. Thousands of these pale rubber loaves could be produced in a day. The process sounds orderly when described step by step. Building it at national scale was not orderly. Plants had to be located near feedstocks, power, water, rail lines, and existing industrial skill. Construction competed with every other war program for steel, copper, valves, instruments, pumps, and workers. Chemical plants could not be improvised safely. Butadiene was flammable. Polymerization could release heat. Pressure systems had to be reliable. A bad seal, contaminated vessel, or a control failure could stop productions or cause disaster. Initial plants were completed and started in months rather than years. Firestone produced the program's first bale in April 1942. Goodyear followed in May. United States Rubber began production in September, and Goodrich in November. Together, those early operations produced only a little more than 2,000 tons in 1942. That was far below national need, but it proved the chain could function. Then the larger government-financed plants came online. Across the country, workers entered a new industry whose vocabulary had barely existed in American mass production. Operators learned reactors. Laboratory technicians tested viscosity and solids content. Maintenance crews kept compressors and pumps running. Railroads moved tank cars of monomers and boxcars of finished bales. Tire factories rewrote mixing schedules. Women entered laboratories, production floors, inspection departments, and tire plants in large numbers. Black workers were employed in chemical and supporting industries, often while facing segregation and unequal opportunity. Communities near new plants experienced housing shortages, crowded transport, and rapid population growth. The emergency industry was built not by an abstract alliance of corporations, but by tens of thousands of people working long shifts around hot equipment and volatile chemicals. Yet, even when the bales accumulated, the real test had not begun. The nation did not need warehouse rubber. It needed tires that would not fail. GRS resisted abrasion well, which made it promising for tread. But compared with natural rubber, the early material was less tacky in its uncured state. Tire construction depended on layers sticking together before vulcanization. If the components shifted during building, the tire could contain hidden weaknesses. Manufacturers had to change adhesives, mixing methods, accelerators, antioxidants, carbon black grades, and processing conditions. Natural rubber also handled repeated flexing and heat in ways that were difficult to duplicate. Early synthetic truck tires could build excessive internal heat. Under heavy load, flexing converts mechanical energy into heat within the rubber. If the heat cannot escape, temperature rises, bonds weaken, layers separate, and the tire can fail. Aircraft and large military tires were especially demanding. For some critical uses, limited natural rubber remained indispensable and had to be carefully allocated or blended with synthetic material. This is an important correction to the popular version of the story. American chemists did not suddenly invent a perfect replacement and end the crisis. They created a workable material, then spent the war learning where it could be used alone, where it needed natural rubber, and how tire design had to change around it. Carbon black became crucial. It is a fine form of carbon that reinforces rubber dramatically. Different grades alter strength, abrasion, heat generation, and processing. The correct polymer, without the correct carbon black, could still produce a bad tire. The rubber program therefore required coordination beyond rubber plants into carbon black production and compound design. Testing became industrial science. The National Bureau of Standards improved methods and instruments so that material from different plants could be compared. Viscosity tests helped predict processability. Chemical analysis measured residual monomers and composition. Tire dynamometers ran tires under controlled loads and speeds. Road fleets accumulated miles. Failures were cut open and studied. The program generated thousands of technical reports. The Library of Congress now preserves a collection containing roughly 8,000 reports and tens of thousands of index cards covering research meetings, processes, standards, plant design, and tire tests. That archive reveals what the victory really looked like. Not one brilliant discovery, but a relentless accumulation of measurements, corrected recipes, failed tires, committee decisions, and shared data. The common recipe itself evolved. Researchers learned how polymerization temperature affected performance. Later work showed that producing SBR at low temperature created tougher, longer-wearing rubber with improved properties. That cold rubber development became commercially important after the war, but its roots lay in the same collaborative research structure. During the emergency, even small improvements had enormous value. A few percent increase in reactor yield meant thousands of additional tons. A processing change that reduced mixing time freed tire capacity. A better antioxidant extended storage life. A test that detected bad material before it entered a tire prevented field failures and saved scarce labor. By 1944, the synthetic plants were producing enough material to meet the central emergency. By 1945, American synthetic rubber capacity had reached roughly 920,000 tons a year, with GRS representing about 85%. Plants designed for lower output were pushed beyond their rated capacity. In May 1945, GRS facilities reportedly operated at about 128% of design capacity. The numbers were extraordinary, but the final product still had to prove itself on roads and runways. By the end of 1945, synthetic passenger tires could equal or exceed the mileage of average pre-war natural rubber passenger tires. Between 85 and 90% of American rubber consumption that year was synthetic. The shortage had not merely been survived. A new material had been trained for mass use. What did that mean in the war itself? It meant tires for the trucks that carried fuel, food, ammunition, and replacement parts. It meant rubber components in the vast fleets moving along the Red Ball Express after the Normandy invasion. It meant Jeep tires, aircraft tires, tank track pads, hoses, seals, electrical insulation, life rafts, gas mask components, medical goods, and machinery belts. Rubber rarely appears in battlefield photographs as the decisive object. The camera sees the tank, not the seals in its engine. It sees the bomber, not the flexible hose and vibration mounts. It sees the convoy, not the chemistry in every tread block. But a mechanized army is a system of repeated motion, and repeated motion destroys rigid connections. Rubber absorbs shock, maintains contact, seals fluids, isolates vibration, and allows parts to move relative to one another. The wartime synthetic product was especially valuable because it released natural rubber for applications where natural performance remained necessary. Every passenger or light-duty product that could use GRS preserved scarce plantation rubber for aircraft tires, heavy truck service, specialized engineering components, and blends requiring resilience. The program also insulated strategy from geography. Japan had captured plantations, but it could not capture American petroleum fields, chemical engineering knowledge, or the factories rising across the United States. The original vulnerability had been a biological supply chain concentrated in tropical Asia. The synthetic program converted that vulnerability into an industrial supply chain spread across refineries, chemical plants, laboratories, and tire factories. That did not make the system simple. It made it controllable. The program's scale can be understood by comparison. NIST has noted that the nation spent as much on the rubber program as it did on the atomic bomb. The comparison is not exact in every accounting method, but it captures the magnitude. The Manhattan Project built a secret weapon. The rubber program built an open industrial ecosystem whose output was distributed through almost every branch of the military. There was also a strategic lesson in cooperation. Before the crisis, American companies possessed fragments of the solution. Standard Oil understood petroleum routes to butadiene and controlled access to important Buna-related knowledge. Tire companies understood compounding and manufacturing. Universities understood polymer chemistry. Government laboratories understood measurement. No participant could solve the emergency alone. The requirement to share patents and data reduced duplication and accelerated improvement. It was not a permanent abolition of competition. It was a temporary recognition that the national bottleneck sat between institutions as much as inside them. The lesson would echo through later American programs in aviation, electronics, spaceflight, and computing. When a technical goal is urgent, the architecture of collaboration can matter as much as the underlying invention. But victory created a new question. What happens to an emergency industry after the emergency ends? In August 1945, military demand fell abruptly. Natural rubber plantations returned to Allied trade. Government contracts were reduced. Synthetic rubber inventories were high. Plants that had operated at maximum speed faced uncertainty. At first, natural rubber regained ground. It was familiar, often easier to process, and once again available at competitive prices. Some observers expected synthetic rubber to shrink into a strategic reserve material, but the wartime industry had changed the economics permanently. Plants existed. Engineers understood them. Tire companies had redesigned processes. Researchers knew how to improve the polymer. The United States no longer had to begin from zero. Post-war research attacked the weaknesses of hot polymerized GRS. One major advance was cold polymerization, carried out near 5 degrees Celsius rather than the much warmer wartime process. New redox initiator systems allowed the reaction to proceed at low temperature. The resulting cold rubber had better wear and mechanical performance and became a superior tire material. Oil extension allowed manufacturers to incorporate processing oils into certain rubbers, lowering cost and adjusting properties. Solution polymerization later offered more precise control of molecular architecture. Chemists learned that synthetic rubber was not one product. It was a platform. By changing monomers, ratios, catalysts, temperature, chain structure, fillers, and cure systems, they could design elastomers for particular jobs. The Korean War again demonstrated the value of domestic capacity. Strategic demand returned, and government plants remained important. In the mid-1950s, the federal government sold most of its synthetic rubber facilities to private industry. The emergency network became a normal commercial sector, though one shaped permanently by government investment and shared wartime research. GRS was renamed SBR, styrene butadiene rubber. The new name removed the government label but retained the chemistry. SBR became the largest volume general-purpose synthetic rubber, especially important in tire treads. It was often blended with natural rubber or other synthetics rather than used alone. That blending is another reason the simple story of replacement is misleading. Modern tires are engineered composites. Their performance comes from combining different materials, each handling a different demand. Natural rubber remains essential because its molecular structure gives exceptional strength, resilience, and fatigue resistance. Synthetic rubber remains essential because it offers scale, consistency, abrasion resistance, aging performance, oil resistance, gas impermeability, weather resistance or temperature capability, depending on the type. The true legacy of the wartime program was not that artificial rubber defeated natural rubber. It was that engineers learned to choose and combine elastomers by function. Walk through a modern tire in cross-section, and the descendants of that idea appear everywhere. The tread may contain solution SBR and polybutadiene, formulated for grip, rolling resistance, and wear. Natural rubber may reinforce regions subjected to severe fatigue. Halobutyl rubber forms an inner liner that slows air loss. Specialized compounds bond rubber to steel belts and textile cords. Silica, carbon black, oils, sulfur, antioxidants, accelerators, and resins shape the behavior. The object looks like one black ring. Chemically, it is a layered machine. Beyond tires, the synthetic rubber family expanded into materials whose properties would have seemed almost custom-made to wartime chemists. Nitrile rubber produced from butadiene and acrylonitrile resists oils and fuels. It appears in fuel hoses, seals, O-rings, industrial gloves, and equipment that would quickly swell or soften ordinary rubber. Butyl rubber, a copolymer based mainly on isobutylene with a small amount of isoprene, has very low gas permeability. It became essential in inner tubes and tire inner liners. Modern butyl and halobutyl materials also serve in pharmaceutical stoppers, hoses, sealants, roofing, vibration control, and protective products. EPDM, made from ethylene, propylene, and a DNA, resists weather, ozone, heat, and aging. It appears in automotive weather seals, roofing membranes, hoses, gaskets, electrical insulation, and outdoor products. Polybutadiene offers low heat buildup and strong wear performance, making it valuable in tires and impact-resistant plastics. Neoprene retains importance where oils, weather, flame, and demanding environments must be managed. Silicone elastomers operate across extreme temperatures. Fluoroelastomers resist aggressive chemicals and heat in aerospace and industrial systems. This diversity explains why the industry did not disappear when Southeast Asian natural rubber returned. Synthetic elastomers could be tailored for environments where natural rubber was unsuitable. The wartime substitute became a family of specialized materials. The scale is now global. Market estimates vary because some reports count raw synthetic rubber, while others include liquid rubber, specialty elastomers, compounds, or downstream products. Recent estimates place the worldwide synthetic rubber market somewhere around the high 20s to mid-30s of billions of dollars annually. Whatever boundary is chosen, the conclusion is the same. This is not a surviving historical niche. It is a major industrial sector. Tires remain the dominant application. That connects the 21st century industry directly to the emergency of 1942. The central question is still how to produce a material that grips, flexes, wears slowly, manages heat, and can be manufactured by the millions of tons. But the optimization targets have changed. Modern tire engineers must balance wet braking, snow traction, tread life, noise, rolling resistance, high-speed stability, and energy efficiency. Electric vehicles add new pressures. They can be heavier than comparable combustion vehicles and deliver strong torque immediately, increasing tire demands. Lower rolling resistance can extend vehicle range, but a compound that reduces energy loss must still grip wet pavement and resist wear. No single rubber provides every property. Chemists adjust styrene content, vinyl structure, molecular weight distribution, branching, coupling chemistry, fillers, and oils. Solution SBR allows more control than the wartime emulsion product. Silica and silane systems can improve the balance between wet grip and rolling resistance. Computer modeling and automated process control now manage reactions that wartime operators watched with analog instruments and laboratory tests. Yet the family resemblance remains. Butadiene and styrene still enter polymerization systems. Latex or solution still becomes polymer. The material is still compounded, reinforced, cured, and tested. The chain from molecule to tire still requires chemistry, mechanical engineering, quality control, and large-scale manufacturing. The industry also carries a difficult legacy. Most synthetic rubber begins with fossil-derived feedstocks. Its production consumes energy and involves chemicals that must be controlled carefully. When tires wear, the rubber does not simply vanish. Friction creates tire and road wear particles containing mixtures of natural and synthetic rubber, carbon black or silica, oils, sulfur compounds, zinc, and road minerals. United Nations and environmental agencies now identify tire wear particles as one of the most abundant forms of primary microplastic pollution. Some remain near roads. Others enter stormwater, soil, rivers, or the atmosphere. The problem does not disappear when vehicles become electric because every road vehicle still needs tires. This creates a new version of the old engineering challenge. During World War II, the objective was survival. Make enough rubber fast enough to keep the nation moving. Today, the objective is more complicated. Maintain safety and mobility while reducing fossil dependence, emissions, toxic additives, wear particles, and end-of-life waste. Recycling cured rubber is difficult because vulcanization creates crosslinks between polymer chains. A tire cannot simply be melted and remolded like a common thermoplastic. Used tires can be retreaded, ground into crumb, used in engineered products, processed through pyrolysis, or subjected to devulcanization research. But each route has technical and economic limitations. Researchers are exploring bio-based butadiene and styrene, renewable fillers, recovered carbon black, improved tire durability, lower wear compounds, and circular manufacturing. Natural rubber alternatives such as WWII are again receiving attention because they could diversify supply and reduce dependence on imported, heavier rubber. The same desert shrub studied in the wartime emergency has returned as a possible modern strategic crop. There is an irony here. Synthetic rubber was created to escape dependence on a vulnerable biological resource. Now the industry is looking again to biology, recycling, and renewable chemistry to escape dependence on fossil feedstocks and reduce pollution. The solution will probably not be a complete return to natural rubber or a complete victory for synthetic rubber. As in modern tires, the answer will be a designed combination. The wartime program offers both inspiration and warning. The inspiration is that a seemingly impossible material shortage can be answered when government, industry, universities, and laboratories share risk and knowledge. In 1941, the United States produced only a tiny amount of general-purpose synthetic rubber. 4 years later, it operated a continental production system approaching 1 million tons of annual output. The warning is that emergency scale can lock in consequences for generations. The plant solved a strategic crisis, but they also helped normalize a petrochemical material economy whose environmental costs were not fully understood. A technology can be essential, successful, and still create the next problem. That is why the story matters beyond rubber. It shows the difference between invention and industrialization. Buna-type chemistry existed before Pearl Harbor. American companies had pilot materials. The breakthrough was not one molecule discovered in a dramatic moment. The breakthrough was the ability to connect patents, feedstocks, reactors, standards, workers, railroads, tire factories, and military demand into a system. It shows the value of standardization. The mutual recipe allowed hundreds of organizations to improve one shared platform. Uniform tests made production from different plants comparable. Standard bales could enter existing factories. The nation did not eliminate variation by decree. It created measurements that made variation visible. It shows why manufacturing knowledge is strategic. A country may possess a patent and still be unable to produce the material at useful scale. It may own a laboratory sample and still lack monomers, catalysts, trained operators, quality control, or downstream factories. Capacity is a form of knowledge stored in equipment, routines, suppliers, and people. And it shows that materials shape history quietly. Battleships, bombers, tanks, and trucks receive names. Rubber compounds receive codes. Yet the named machines cannot function without the anonymous material. In 1942, an American family rolling an old tire to a gas station collection pile could not see the chemical industry rising behind the propaganda posters. A refinery worker producing butadiene could not see every truck that would use the final tread. A university chemist measuring polymer viscosity could not see the convoy crossing France. A woman operating a tire-building machine could not see which aircraft would land on the product of her shift. But their work connected. The rubber crisis began because the United States had placed the mobility of its economy and military in the latex of trees thousands of miles away. The solution was not elegant. It involved ration books, scrap piles, political fights, delayed plants, imperfect tires, dangerous chemicals, and constant testing. It required natural rubber to be conserved, synthetic rubber to be improved, and both materials to be used where each performed best. By the end of the war, the emergency material had become dependable enough to carry most of the national load. After the war, researchers made it better. Private industry absorbed the plants. New elastomers multiplied. The substitute became infrastructure. Today, the black tread touching the road is the visible edge of that history. Inside it are polymers descended from wartime GRS, other synthetics developed before and after the conflict. Natural rubber still harvested from trees, reinforcing fillers, steel, textiles, oils, and chemical systems tuned to work together. The tire is not proof that synthetic rubber replaced nature. It is proof that the crisis taught industry how to engineer elasticity. The world created by that lesson is enormous. It turns in billions of tires, seals millions of machines, protects medicines, insulates buildings, carries fluids, absorbs vibration, and supports a market worth tens of billions of dollars. Much of it traces back to the months when America faced a simple, terrifying calculation. The stockpile was shrinking faster than a new supply could arrive. Every revolution leaves behind objects that seem ordinary only because the revolution succeeded. The rubber hose, the black tire, the window seal, and the medicine stopper attract no attention precisely because failure is rare. Their quiet reliability is the commercial form of lessons learned under emergency pressure. Control the molecule, measure the variation, test the finished product, and never trust a laboratory success until it survives the road. That discipline, more than any single recipe, is the enduring wartime inheritance today. The country responded by building molecules at the speed of war, and the industry never stopped.